Why is the ocean salty, but rivers aren't? One mouthful of seawater is enough to make most people spit it out. It's far too salty to drink. But here's the strange part. Almost every drop of that seawater arrived through rivers, and rivers are fresh enough to drink in many places around the world. So where did all that salt come from? If rivers keep filling the ocean, why doesn't the ocean slowly become fresh? And if rivers really are fresh, who put billions upon billions of tons of salt into the sea in the first place? The answer isn't hidden in one place or one moment. It's written across mountains, rivers, volcanoes, and even the deep ocean floor. And it's a story that has been unfolding for billions of years. Long before scientists understood chemistry, people invented stories to explain the salty sea. Some believed giant creatures spilled salt into the water. Others imagined magical mills grinding endless piles of salt beneath the waves. These tales sounded impossible, yet they all tried to answer the same mystery. At first glance, one explanation seems obvious. Maybe the ocean simply started salty. But that doesn't solve the puzzle. Even if Earth's earliest oceans contained some dissolved minerals, scientists know the chemistry of those ancient seas was probably very different from today's. The exact composition is still an active area of research. So something else must have shaped the ocean we know now. The real clue comes from something so ordinary that we rarely notice it: rain. Rainwater looks perfectly pure, but it isn't completely pure. As it falls through the atmosphere, it dissolves a small amount of carbon dioxide, making it ever so slightly acidic. Not enough to harm us, but enough to begin a slow chemical attack on rocks. Imagine millions of tiny invisible chisels tapping away at mountains day after day, year after year. Every raindrop removes only a microscopic amount of material. You could watch a rock for your entire lifetime and never see the difference. But Earth has had billions of years to wait. As rainwater flows across the land, it slowly dissolves tiny amounts of minerals from rocks. These minerals break apart into charged particles called ions. If that sounds complicated, think of them simply as tiny building blocks released from stone. The water carries these invisible passengers into streams. Streams join rivers, and rivers eventually reach the sea. Here's the twist. Rivers are not completely fresh. They contain dissolved minerals all the time. The concentration is simply so low that most people can't taste them. Around the world, scientists measure these dissolved ions in rivers every day, and the evidence is clear. Every river is quietly transporting tiny amounts of Earth's crust toward the ocean. In other words, every rainfall is slowly carrying away pieces of mountains. Now imagine this happening everywhere on Earth, every single day, for billions of years. Suddenly, those tiny amounts no longer seem so tiny. But another mystery appears. If rivers keep bringing dissolved minerals into the ocean, shouldn't rain eventually wash the salt back out again? Surprisingly, it can't. When sunlight warms the ocean, water evaporates into the atmosphere. The water molecules escape as vapor, later forming clouds and eventually falling as rain. The dissolved salts don't evaporate with them. They stay behind. It's a bit like boiling a pot of water on the stove. As steam rises, the water disappears, but the salt remains in the pot. Keep adding more salty water and boiling away only the water, and the remaining liquid becomes saltier. The ocean has been doing something similar on a planetary scale for an unimaginably long time. Today, the average ocean salinity contains about 35 parts of dissolved salts for every 1,000 parts of seawater. That's roughly 3.5%. But even that raises another question. Rocks contain many different minerals, so why is seawater dominated by ordinary table salt, mostly sodium and chloride, instead of a balanced mixture of everything? The answer lies in what happens after minerals reach the sea. Many dissolved elements don't stay in seawater very long. Marine organisms use calcium to build shells and skeletons. Other minerals become trapped inside new rocks or settle into sediments on the ocean floor. Sodium and chloride behave differently. They are much less likely to be removed quickly, so they remain dissolved for much longer. Over immense stretches of time, they become the dominant ingredients in seawater. Yet rivers aren't the whole story. Far below the surface, hidden beneath kilometers of water, another process has been quietly shaping ocean chemistry all along. The seafloor is far from lifeless. In many places, seawater seeps deep into cracks in Earth's crust. As it approaches hot rocks heated by magma, it becomes superheated and reacts with the surrounding minerals. The water then rises back through hydrothermal vents, sometimes called black smokes, carrying dissolved chemicals into the ocean. Submarine volcanoes also release minerals directly into seawater. So the ocean isn't simply collecting material washed off the continents. It is constantly exchanging chemicals with the planet itself. Land and sea are connected in ways that are almost impossible to see from the shoreline. At this point, you might wonder why the ocean hasn't become endlessly saltier. After all, rivers never stop flowing. Volcanoes never completely stop erupting. Shouldn't the salt keep building forever? For a long time, scientists wondered the same thing. The answer is that Earth also has ways of removing salt. Some dissolved minerals become locked inside marine sediments. Others react with the oceanic crust during hydrothermal circulation. Tiny marine organisms help move certain elements from seawater into the rocks that eventually form the seafloor. The ocean isn't filling like a bathtub with the drain closed. It's more like a giant recycling system, where materials are constantly entering and leaving through slow geological processes. That's why average ocean salinity has remained relatively stable over millions of years, even though it has changed throughout Earth's long history. The balance isn't perfect, and local conditions can be very different. Some places receive heavy rainfall or large amounts of river water, making the surface less salty. Elsewhere, intense evaporation removes water faster than it is replaced, concentrating the salt. That's why enclosed bodies of water, like the Dead Sea, are far saltier than the open ocean. Water escapes mainly through evaporation. Dissolved salts have nowhere to go. Ocean salinity also does far more than affect taste. Salt changes the density of seawater. Dense, salty water sinks, while less salty water stays closer to the surface. These slow movements help drive global ocean circulation, transporting heat around the planet and influencing weather, climate, and marine ecosystems. In other words, the salt in the sea helps shape life on Earth itself. Now imagine something almost impossible to picture. If you could remove every grain of dissolved salt from the world's oceans and spread it evenly across Earth's continents, it would create a layer roughly 166 meters, or more than 500 feet thick. All of that came from countless tiny chemical reactions repeated over billions of years. Not from one event, not from one volcano, not from one river, but from the patient work of an entire planet. The next time a wave reaches your feet, you're experiencing far more than salty water. You're tasting rain that slowly dissolved ancient mountains. You're tasting rivers that carried invisible minerals across continents. You're tasting chemicals exchanged deep beneath the seafloor, where hydrothermal vents still reshape the ocean today. You're tasting a planet that has never stopped changing. The ocean isn't salty because someone filled it with salt long ago. It's salty because Earth has been writing its own history, one raindrop, one river, one volcano, and one wave at a time.